Welcome back to The Explainer. Okay, today we are tackling one of the coolest spatial puzzles in human history. I mean, think about it. How do you take our massive, infinitely complex three-dimensional world, with all its towering mountains and plunging valleys, and somehow squash it perfectly flat onto a 2D piece of paper? It honestly sounds impossible, right? But as we'll see, map makers actually figured out a brilliant system to do exactly that.
Okay, let's dive right into this. We're going to build our map reading skills logically today. We'll start by looking at our diverse 3D world, decode the language of maps, figure out how to measure from sea level, explore colors and contour lines, and finally, look at why topography actually matters in the real world. So, step 1, let's look at our incredibly diverse 3D world, from mountains all the way down to the deserts. Before we can even begin to understand how to read a map, we really have to appreciate the sheer physical variety of the planet that cartographers are trying to capture. Just look at this stark contrast. On one hand, you have an oasis in the blazing hot Sahara Desert. On the other, the freezing, ice-covered continent of Antarctica. Our world is wonderfully varied, with mountains, seacoasts, deserts, and forests. And capturing all these variations on a map isn't just about drawing pretty pictures, it's fundamentally about understanding how these different Earth surfaces directly affect the lives, the climates, and the agriculture of the people who actually live there.
Which brings us to our second section, the language of maps, specifically how we use symbols and scales.
To represent all those wild, real-world variations on flat paper, map makers literally had to invent a universal visual language. They take physical objects and translate them into what we call symbols. Remember, a map isn't just a photograph, it's a symbolic representation. So cartographers basically use three primary types of markers to show things: point symbols, line symbols, and area symbols. And these are often filled with distinct colors or patterns to make them immediately pop out to the reader.
Let's walk through some concrete examples of how this translation actually works. Say a map maker wants to pinpoint a specific city, like Delhi. They'll use a point symbol, usually just a simple dot. Now, to represent a flowing body of water, like the River Manjira, or maybe a railway track, they draw a line symbol along its course. And if they need to demarcate something larger, like the boundary of a playground, or even an entire district, like Hyderabad, they draw a boundary and fill it in. That's an area symbol.
But, just drawing the shapes isn't quite enough, is it? We need to know the actual distance between them, and that is exactly where scale comes in. Take this map, for example. The scale tells us that 1 centimeter on the paper equals 200 kilometers out in the real world. So, by just grabbing a simple ruler, you can accurately measure the massive real-world distance between, let's say, Hyderabad and Jaipur, right there sitting at your desk. It's a pretty powerful tool.
Okay, so points, lines, and scales work perfectly for measuring flat distances. But here is the ultimate cartographer's dilemma. How on earth can we represent the heights of land, that full 3D topography, on a completely flat piece of paper?
Now, what's really interesting about this slide is the core problem of drawing mountains. You might initially think, well, just draw a 3D picture of the hill. But as you can easily see, a normal 3D drawing naturally hides whatever is behind that mountain. If there's a little village tucked back there, you completely miss it. It's totally useless for navigation. A true map, however, has to show a top-down view where absolutely everything is visible, flatly, without anything hiding.
That perfectly tees up Section 3, measuring from sea level, which gives us our global starting line. See, before cartographers can even attempt to show height from a top-down view, they need a starting point, a universal zero. And because all the oceans in the world are connected, the top surface of the sea is taken to be roughly the same everywhere on the globe. But there's a catch, right? The sea never stands still. You've got constant high and low tides. So to get a true, reliable zero, scientists carefully measure the sea level at frequent intervals over a long period of time and then calculate an average. This globally recognized starting point is what we call mean sea level, or MSL.
Let's actually look at a cross-section of a fictional place, let's call it Nimpur Village, to see this in action. The water over on the right, that's our mean sea level, sitting exactly at 0 meters. Now, as we move inland and head uphill, we can see exactly how height is calculated. Nimpur Village sits nicely at 50 meters above sea level, and that temple, way up on the peak, is towering above at over 100 meters.
All right, moving right along into Section 4, colors and contour lines, or how we actually map that elevation. Now that we finally have our heights measured from a solid zero, How do we show them flat without hiding anything behind the mountain? Well, the first clever technique cartographers use is color, and this brilliantly illustrates the concept. They basically take that cross-section we just saw and slice it into specific height zones, and then they assign a specific color to each of those zones.
For example, any land that falls between 0 and 50 meters might be painted green. Land between 51 and 100 meters, that gets painted yellow. And the highest land, everything from 101 up to 150 meters, is painted brown. So, when you're looking at a physical map and you spot a brown area, you instantly know that specific region is over 100 meters above sea level. It is a remarkably simple, yet totally intuitive system.
But sometimes you need a lot more precision than just broad color zones. And for that, we turn to contour lines. This is kind of like a giant puzzle, but there are 3 vital rules to solving it. Rule 1. A contour line joins all places on the map that share the exact same height. Rule 2. Because a single point on the actual ground can't be 2 different heights at once, contour lines can never ever cross each other. And Rule 3. The distance between those lines actually tells you about the steepness of the slope.
Let's move on and see how this all builds into our final top-down view of Nymper. Notice that irregular loop passing right near the village? That's the continuous 50-meter contour line. It perfectly outlines the shape of the landform at that exact height. And remember Rule 3? If you see lines drawn very close together, you're looking at a steep climb. But if the lines are spaced far apart, the land there has a gentle, easy slope. You are quite literally reading 3D terrain on a 2D piece of paper. How cool is that?
Which brings us to our final part, Section 5. Why topography matters and how we actually use these height maps out in the world. So, we've decoded the map maker's secrets. But why does this all matter? Why do we care so intensely about exact heights and slopes? Well, it's absolutely crucial because human infrastructure completely depends on it. Reading these height maps lets us identify the true nature of the terrain. I mean, if you're an engineer planning a massive road construction project, you need to know exactly where the gentle slopes are so cars can travel safely. If you're building a dam, you absolutely must pinpoint exactly where the deep valleys are located to capture the water.
To put this into perspective with a real-world geographic example, let's consider the Telangana Plateau. If you look at a physical map showing height for this region, you can clearly trace the Godavari slopes over in the east. Then, as you move west, the map reveals the hills of the plateau region. It beautifully illustrates how rivers, like the Krishna and Godavari, have carved deep, broad valleys straight through that high terrain. Without a height map, this incredible dynamic 3D landscape would just look like a flat, totally featureless shape.
So there you have it, the cartographer's dilemma completely solved. Through the ingenious use of mean sea level, color zones, and those intricate contour lines, an entire 3D world is perfectly preserved on a single, flat sheet of paper. So my final question to you is this. Next time you look at a flat map, will you just see a bunch of lines and colors, or will you actually be able to see the mountains rising right off the page? Thanks so much for joining me for this explainer. Keep exploring, and I'll catch you next time.